My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Uh, Good morning to all here in Bangladesh, and a very good evening to all those who are watching this program live from USA. So this is very a new type of experience we are having, and we are staying in a corona pandemic situation. As we know that all the institutions have been shut down due to the COVID since last year. So we cannot continue our normal academic program inside the campus. So we have to actually start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including a new type of webinar. It's the International Physics webinar, and we have successfully completed our 171st International Physics webinar. And this is our 172nd International Physics webinar. And today I'd like to welcome you all to a joint session between our department, Department of Physics, Pabna University of Science and Technology, and the Department of Physics and Astronomy, Texas Tech University, Texas, USA. And we have with us here today Dr. Tom Maccarone, sir, Professor, Department of Physics and Astronomy, Texas Tech University, Texas, USA, and he has already connected with us, sir. Good morning and good evening to your part. Thanks for accepting our invitation, sir, and thanks for giving us this opportunity to arrange such an important webinar with us. So, I think you have already come to know the title of this today's International Physics webinar. Title is very exciting: The Searches for Black Holes in the Galaxy. And our speaker is Dr. Tom Maccarone, Professor, Department of Physics and Astronomy, Texas Tech University, USA. And you can see his educational and professional background. He has completed his bachelor degree in physics in 1996 and MS MPhil in astronomy from the California Institute of Technology and PhD degree from the Department of Astronomy. And we can see his professional experience. Texas Tech University, Texas, Presidential Research Excellence Professor, Department of Physics and Astronomy from 2018 to present time, and Professor, Department of Physics and Astronomy, August 2017 to August 2018, Associate Professor, Department of Physics, January 2013 to August 2017, University of Southampton, UK, lecturer, then reader, School of Physics and Astronomy, July 2005 to December 2012, and postdoctoral researcher, SISSA, uh, from November 2001 to 2003, and Yale University, New Haven, researcher from 1997 to 2001, and Jet Propulsion Laboratory as a research fellow, June 1994 to August 1994. We can see his research interest, compact object populations, and especially in global clusters, accretion, the ejection physics, and time series analysis methodology. So honors and awards: integrated scholar designation from the Texas Tech for faculty who integrate teaching, research, advertise and activities together, 2020, and Professor of the Year Award, Texas Tech Society for of Physics Student, 2007-2019, Drake Brower Prize from Yale University in 2003, Harriet Smith Fellowship in Astronomy from Yale University, Doris A. Purple Speaking Awards, Caltech 1995, Dewton Memorial Scholarship, Caltech 1993, and Stephen David Jocknoids Scholarship 1992, and Swamport Work Memorial Scholarship 1992. And this is his Google Scholar ID. His citation is more than 13,000, and this is his Inspire ID. This is his selected publication list. So thanks for all of your patience. Now it's time to go to our speaker, sir. I'd like to welcome you again. It's your time, sir. You can start your session.
Okay, so thank you very much for having me. And I can only see my screen, so I can't see you all. But if there's some way that you can alert if there's a clarification you need in the middle of the presentation, I don't mind short interruptions as I'm speaking, especially because it's a little past 10 p.m. today where I am, and I'm a little bit tired, so I may accidentally forget something. So I'm going to do my best here. All right, so just as an overview, I'm going to talk about what black holes are, why we shouldn't see them, and then how we go about finding them anyway. And I'm going to talk about this in a variety of contexts in the Milky Way galaxy. And just as a note, the references I'm giving on the slides are for the sources of the images where they're not popularization images. And often the image that looked the nicest isn't the one where the foundational work was done. So if you want to do some further reading on some topic that I talk about and you aren't quite sure where to start, feel free to send me an email and I'll get back to you probably within a day or two. All right, so let's talk about a little bit of a history of black holes. So there's a guy named John Mitchell, and he's actually, I would say, one of the most important but least known scientists that we have in the history of physics. So he did a whole bunch of things. He was one of the first people to apply statistics to astronomy. He was one of the first people, he came up with the idea for using a torsion pendulum to measure the universal gravitational constant. And then he ended up dying before he was able to actually use it. And he also did some foundational work in geophysics. But what's relevant for our talk today here is that he, in 1783, came up with the idea of a black hole. So what he suggested was that a star that was about 500 times the size of the sun, but with the same density, would have an escape speed faster than the speed of light. And so his statement turns out to be correct, but the reasoning is flawed. But it was still a big idea that we owe a certain debt to. All right, so it turns out if you use Newtonian physics and you set the escape speed equal to the gravitational potential energy, or sorry, if you set the kinetic energy equal to the gravitational potential energy and solve for the escape speed using Newtonian physics, you get the correct answer for the Schwarzschild radius that you would get from doing general relativity, and that's just a coincidence. Right, and so when you have a spinning black hole, this analogy breaks down. But the idea that you might create a body that light couldn't escape from is one of the ones that helps us towards the idea of a black hole. It was quite a long time before Einstein and then Schwarzschild in the early 1900s came up with the equations of general relativity and then the particular solution that leads us to understand that there really are objects that we now call black holes from which light can't escape. And a little later on, Roger Penrose came up with the real proof that these really were objects and not just some fictitious solution to Einstein's equations. And Penrose won last year's Nobel Prize for that theoretical part of the work, and the observational part of the work was the other part of that Nobel Prize. All right, so now I want to do a little bit of a refresher on stellar evolution and talk about the lives and deaths of stars. And it could be that you all have already heard this before, but I figured it's better to give some information that you've already heard before than to accidentally leave out an important part of the story. Okay, so this diagram is a color magnitude diagram for stars. And so we have luminosity on the y-axis, and we have the temperature of the stars on the x-axis. And we see this locus of stars here, which we call the main sequence. We see this locus here called white dwarfs, and then we have giants and supergiant stars. All right, now here, what we can see is what the long-term evolution of a star looks like as a function of the star's mass. And by the way, can you all see my mouse cursor? Yes? No?
Yes, we can see it.
Okay, good. All right. Okay. So for low mass stars, well, the lowest mass objects will be brown dwarfs. And so they'll start off as a protostar, collapse into a brown dwarf, and they'll stay that way for essentially the whole age of the universe. As we move up in stars to stars like, in lower mass stars, they'll turn into a red dwarf and then gradually turn into a white dwarf. It will move to intermediate mass stars like the sun. They'll turn into a red giant, have a planetary nebula ejection in a lot of cases. In some cases, we might not see that, and then leave a white dwarf behind. But as we go up to more massive stars, the stars will end their lifetimes with supernova explosions. And so for the stars more than about 8 times the mass of the sun, they'll have some kind of supernova explosion, and most of the time they'll leave behind a neutron star after the supernova. But as you go to even more massive stars, they can end up leaving behind a black hole as a result of a supernova, or maybe even without a supernova in a prompt collapse of a massive star into a black hole, right? And so the connection between these plots is that here stars are fusing hydrogen in their cores, but gradually they run out of hydrogen, and then the core collapses, but then the envelope expands, and that's when we get these giant and supergiant phases. And in those phases, you'll end up burning through the heavier elements. And eventually, once you reach iron, nuclear fusion will no longer provide energy, and then there's no pressure support against gravity, and the star will collapse. And in some cases, the collapse will release so much energy that it blows the star up. That's when you get a supernova. But in some cases, the collapse will just continue, and you'll collapse into a black hole. And there's still a lot of theoretical debate about exactly when you form black holes and when you form neutron stars in terms of what are the initial masses. Is it a monotonic process where below a certain mass you make a neutron star and above a certain mass you make a black hole? Or is there some back and forth? And a lot of it depends on our understanding of stellar winds, and some of it may depend on whether the star is in a binary system or not, because binary stellar evolution can be a lot more complicated than single stellar evolution, because you could be transferring mass back and forth between the two stars. And in those cases, some of the basic rules that work for single stars may break down. All right, so now I want to talk a little bit about a motivation for why we want to understand the populations of stellar mass black holes in the galaxy. So this is a plot from a paper by Chris Belczynski from a little less than 10 years ago. And the observations have been updated a little bit since then, but the basic picture is still mostly the same. That if we look at the objects that we found, and I'll talk more in a bit about how we found them, we see neutron stars and we see black holes. And the neutron stars are all less than about 2.2 solar masses, and really the ones that are over 2 solar masses are either just barely over, or the measurements aren't very good. And then the lowest mass black holes that we have dynamically confirmed are somewhere around 5 solar masses. And so there's this gap here, right? And in this paper, what they showed is that depending on the assumptions that you make about how quickly the supernova blows up after the core starts collapsing, you can either reproduce this gap, as you see with the rapid plot here, or you can fail to reproduce the plot, as you see with the delayed tracks here. Okay, so we want to get a better handle on whether this gap is real or due to observational selection biases and just limited numbers of objects that we've discovered. Right, and this is a key to understanding supernovae. Okay, so one of the important things to understand here is that if you're trying to understand supernovae, you don't actually want to look at the supernovae themselves. And the reason is that a supernova is basically a big optically thick layer of gas that's being blown out in an explosion. And so all you can really tell from looking at the supernova's light curve or spectra or anything like that in the optical band where people usually study supernovae is how much mass was ejected and how much kinetic energy was input. Everything else gets washed out because it's sitting underneath this incredibly optically thick envelope. Okay, so the way that you can understand supernovae are through neutrinos that might actually escape from the supernova, gravitational waves that can actually escape, all right, and then of course these can pass through almost any amount of gas with almost no absorption in both cases, or the compact remnants, the neutron stars and black holes that get left behind. Now, neutrinos and gravitational waves would, in principle, give you much better information about how the supernova blew up than the mass distribution of the compact remnants. But the problem is that neutrinos and gravitational waves from supernovae can only be studied for the most nearby supernovae and can only be studied while the supernova is happening. These compact remnants are things that we can study billions of years after the supernova happened, And so that's why they're our best piece of evidence with the technology that we have right now for understanding the supernova process, even though they're a quite indirect way of probing it. And so there's a bunch of things that we want to understand about the neutron stars and black holes in order to understand the supernova explosion. The masses are the easiest one to make nice plots of and the easiest ones to measure. But we'd also like to know for the black holes how rapidly rotating they are. And in both cases, we'd like to know what their space velocity is. Because if the supernova is even a little bit asymmetric, a large space velocity to a neutron star or a black hole that formed in that supernova. All right, so now I think I've hopefully convinced you some of the reasons why it's so interesting to go out and find a bunch of black holes and try to understand various things about them. So now let's talk about how we go about doing this, because what we're talking about is kind of seeing gravity, right? So there's a couple approaches that are really directly related to the gravity, and these are techniques that will get more and more use as we go forward, but I'm going to mention these so that then I can go and focus on the electromagnetic searches later. Okay, so one way is if black holes merge in gravitational wave events, then we can look for gravitational waves. And I think you already have talked by Gaby Gonzalez, so I'd imagine that you've all heard that before. And then the other possibility is that you can look for gravitational microlensing events. And the idea here is that if we have black holes floating around in the Milky Way galaxy, every once in a while, they'll pass along a line of sight that's almost directly between a normal star and us. And when they do that, because the rays of light will be bent as they go around the black hole. And what that leads to is making this star look brighter when it's close to the line of sight, right? Because the kind of a way to think about how bright something looks is how densely packed rays of light are for it. And so if you should just have one ray of light coming in here, if you start making all of these rays of light bend onto you because of the gravitational lensing effect, you can magnify the brightness of this star, right? And because the black hole and the star will be moving relative to one another, the magnification will only happen for a certain amount of time. And so by tracking how long that duration of magnification is and how strong the magnification is, and figuring out the distances of the two objects, you could infer that there was a black hole that passed along the line of sight. This technique has a lot of potential, but it hasn't really yielded much. And the main reason is that most of a black hole microlensing event will have a very long duration compared to the microlensing events from other kinds of objects. And so we've seen tons of microlensing events with microlensing surveys. Not very many of them are convincingly black holes. And that's probably mostly because the black hole events take so much longer that it takes a while before you can figure out that you found them. All right, so the most common way that we see gravity in astronomy, though, is by making use of orbits and binary stars. So there's a famous saying by Cecilia Penn-Gaposchkin that 3 out of every 2 stars is a binary. And what she meant by that is if you look at 2 stars on the sky, the chances are that one of them is a binary and one isn't. So for every 2 stars you think you're seeing 3, and that's kind of the origin of this quote. And so when we have binary star systems, there's a bunch of approaches that we can take to understanding that we have a binary. In the best cases, you get visual binaries where you see both stars and you can track their orbits over time. And if you do that, you can use Kepler's laws to work out what the masses of the 2 objects are. Most of the time, it's not that easy. Most of the time, you can only detect one of the 2 objects, or if you have a very wide binary, you see both of them, but their orbits are so slow that you can't really figure too much out directly. And for most of the things that I'm going to talk about, the orbits are really small, and so you can only find them through spectroscopic measurements. All right, so there's about 100 billion stars in our Milky Way galaxy, and we think that there are around 100 million black holes, and not all of the black holes will be in binaries. In fact, because of the supernova explosion, a lot of the systems will become unbound during the supernova explosion. So we'd expect that the black holes are even less likely to be in a binary than the typical star. So what this is saying is that maybe 1 in every 1,000 stars that you look at in the sky has a black hole companion, but it's probably going to be a bit lower than that. And so you don't want to just go out and look at every object and see if you can prove that there's a black hole there. Instead, you want to, the way I kind of put this is really for a needle in a haystack, try to have a magnet. And the magnet that we're going to use here is going to be X-ray emission. All right. Now, the history of X-ray astronomy is quite an interesting one. So X-rays don't get through the Earth's atmosphere. And so we needed space-based astronomy to start doing X-ray astronomy. So the first set of space-based X-ray astronomy was done in the late 1940s and in the 1950s, mostly by a guy named Herbert Friedman, who worked at the United States Naval Research Labs. And X-ray astronomy was enabled at the end of the Second World War. So what happened at that point was that up until the Second World War, the leading country for producing rockets was Germany. And the Germans had a bunch of rockets that, and they used them mostly for military purposes to launch missiles. The Germans had a bunch of leftover rockets that were captured by the Allied forces at the end of the war. And also the German rocket scientists almost all ended up in either the United States or the Soviet Union after the Second World War. Okay, so the United States military seized these rockets and they asked the military research labs to figure out what to do with them. And a certain fraction of these rockets ended up at the Naval Research Labs. The United States Navy has a long tradition of doing astronomy for various reasons. The historical tradition revolves around the fact that using the stars to navigate ships is something that's been done since the ancient Polynesians in, around 3,000 years ago. And it's still important to this day. If people go to officer training school in most navies, they get forced to take some celestial navigation courses, just because if the GPS goes out, you want to have some way that you can navigate a ship. All right. It turns out that the Naval Research Labs have maintained a lot of interest in astronomy in the United States, both because some of the high energy astrophysics detectors have some applications to some security things, and they've realized that it's easier to get people who know about the detectors if you let them do some astronomy than if you try to hire them for purely military reasons. And then in radio astronomy, there's a lot of work that goes on both in the Naval Research Labs and the United States Naval Observatory. In the Naval Research Labs, it's for a similar reason to why they do high energy astrophysics, so that they can work on remote sensing. And the U.S. Naval Observatory is in charge of making sure that we understand how the Earth is rotating, so that we can make GPS work. So if you have a cell phone with a GPS on it, it's actually calibrated using astronomy. Okay, so Friedman, getting back to our story, Friedman decided to slap a Geiger counter on the side of one of these rockets, shoot it up into the atmosphere, and see if he could detect the sun. And they detected the sun in X-rays, but what happened was that our sun is not a very strong X-ray source by the standards of even normal stars. And people did a calculation, and they said, if you took the sun and you put it at the distance of the nearest other star, there was no hope in detecting the X-rays from it. And so what that meant was that for the next decade or so, all of X-ray astronomy was based around looking at the sun. In the early 1960s, what happened was the United States made a commitment that they were going to land a person on the moon by the end of the 1960s. In the early 1960s, since nobody had been to the moon before, nobody knew what the surface of the moon was made of. But there was an influential theoretical astrophysicist named Tommy Gold, who had an idea that there was a thick layer of dust on the surface of the moon. And if that had been the case, then if you landed a rocket on the moon, you'd never be able to take off again, and you'd be sending the astronauts on a suicide mission, and nobody wanted that. So what happened was there were a couple people, Riccardo Giacconi and Bruno Rossi, and they were working in Cambridge, Massachusetts. Rossi was at MIT, Giacconi was working for a company called American Science and Engineering that had some close collaborations with Harvard and MIT. And what they realized was that if you took the X-ray detectors had gotten better by enough that if you took the solar X-rays and they hit the dust on the surface of the moon, you would get fluorescence from it. And they proposed to launch some rockets with much better Geiger counters and point them in the general direction of the moon in order to see if the moon was showing fluorescence. And the moon didn't show fluorescence, but they discovered cosmic X-ray sources in this rocket flight. And this was a 6-minute rocket flight that went just barely high enough above the Earth's atmosphere to detect X-rays. And that was the birth of X-ray astronomy, and that's why Giacconi won his Nobel Prize for starting the field of X-ray astronomy. All right, so now let's talk about what Giacconi found and what we're going to talk about looking for to find black holes. So if we have a close binary star system, what we can have is a star filling its Roche lobe, right? So the Roche lobe is the equipotential surface for a star, and to figure out exactly what it looks like, you have to think about the gravity of this star, the gravity from its binary companion, and the rotation. Okay, and so it has this kind of teardrop shape, and at this point, the inner Lagrangian point, the matter is equally well gravitationally bound to the star it's coming from and the star that it ends up going to. And so if you have a little bit of gas pressure here because the star is hot, then some of the gas will flow. As it flows in, it forms an accretion disk, and the gas in the accretion disk spirals in towards whatever's at the center of the disk. The in-spiral is probably due to magnetic effects in this ionized gas, but it's not fully understood at this time. But as the gas falls in, it's going into a very deep gravitational potential well. And when you go into a very deep gravitational potential well, you end up releasing a lot of energy. And it turns out if you keep this gas in Keplerian orbits as it spirals in, half of the energy has to go into increasing the speed of rotation of the gas, but the other half has to be dissipated somehow, and it gets dissipated as thermal energy. Okay, so we can write down some quick equations that almost correctly deal with this, or we could write down much more complicated equations that do it more correctly. And since this is a talk rather than a paper, I'm going to write down the quick equations. So what we can do is we can say the luminosity is going to be approximately equal to g times the mass of the accretor times the mass transfer rate divided by the radius in the accretion disk. And that's going to be approximately equal to sigma, which is the Stefan-Boltzmann constant, times the temperature to the 4th power, times some characteristic radius squared. And I left a pi out that I should have put in there. All right, so if you solve these equations for the temperature, you'll see some interesting things that happen. But so one of them will be that because for a black hole, the mass is proportional to the radius, and then the maximum mass accretion rate is also proportional to the mass. It'll turn out that for black holes, the more massive the black hole, the cooler the accretion disk. And if we go and solve this for a stellar mass black hole of around 10 times the mass of the sun, what we'll find is that the temperature will be about 10 million degrees Celsius, and that'll give a peak in a spectrum of about 1 kilo-electron volt. And that's in the X-ray band. And if we do this for neutron stars, we'll get a number that's just a little bit higher. Right? So that's in the X-ray band. And there really aren't that many other sources of bright X-ray emission in the sky. So anytime we find a bright source of X-rays, there's a good chance that it's coming from an accreting black hole. All right. Now, the other thing that it could be would be an accreting neutron star. The way that we solve that problem is that neutron stars have some maximum mass, and exactly what it is depends on the pressure-density relationship. So a pressure versus density relationship for an object will give you a mass versus radius relationship. And so we usually express this as a mass-radius relationship because that's what we can measure. But the real physics behind it is the pressure-density relationship. And we don't understand what that should be like for nuclear density matter. So for neutron stars, we're still working on trying to figure out what the maximum mass is, but no reasonable pressure-density relationship for neutron stars will give you maximum mass bigger than 3 times the mass of the sun. So if we go out and look and we find something that's bigger than 3 times the mass of the sun, and it seems to be a bright X-ray source, and there's not an optically bright star there, then we basically know we have a black hole. All right, so now how do we go about getting the masses? Okay, so we need to use Kepler's laws, right? So what we can do is we can find a case where we can measure the donor star, and we can take an optical spectrum of the donor star, and if we repeatedly do that, the Doppler shift on the absorption lines from the donor star will change as the star goes around in its orbit. And this plot kind of illustrates this for one particular object. But then, so if we know the orbital period and the orbital velocity, then we can get a minimum possible mass for the system. But to get the actual mass, we need to figure out what the inclination angle of the binary is, because when we measure the radial velocity of the orbit, we don't measure the part that is along the plane of the sky. And in most of these X-ray binary systems, the wobble on the plane of the sky is too small to measure with current instruments. Okay, so what you need to do is figure out a technique to find the inclination angle. If the system is eclipsing, like in this example, then that makes it actually really easy to figure out what the inclination angle is. Because things only eclipse when they have inclination angles very close to edge on. But if the system doesn't eclipse, then what we need to do is to make use of the fact that we have this teardrop shape for the donor star. And so as the star moves around in its orbit, its brightness will change a little bit. And we call that ellipsoidal modulation, right? And that's illustrated here also, right? So if we look at the star this way, it's a bit brighter, and then here it's a bit brighter, and then it's a bit fainter when we're looking at the teardrop where we're seeing it as a spherical star, or appearing to be spherical. Right? And so if you measure the amplitude of the ellipsoidal modulations, the more edge on the system is, the bigger that amplitude is. And so that gives you a technique that's pretty good for measuring the inclination angles, but usually the accretion disk has some optical light too, and you have to figure out how to correct for that. All right, so now I want to talk about the importance of X-ray transients. And X-ray transients have been known since the 1970s. I just found this 2020 paper with a nice figure. So most of these accretion disks have some instability in them because the ionized gas will have faster inflow than neutral gas. And usually the outer part of the accretion disk will be neutral some of the time. And so you pile up matter for a while until the pressure heating ionizes the gas, and then suddenly you dump a bunch of mass in. And this is a good example of it from a particular X-ray binary. So this is using the Swift Burst Alert Telescope and the Rossi X-ray Timing Explorer all-sky monitor for this system. What you see is you see this big burst of X-ray emission. We call this an outburst. And the source brightens and then fades. Since almost none of the black hole X-ray binaries are persistently bright, this is the way that we find new ones most of the time. And so we probably only found around 1% of the black hole X-ray binaries in the Milky Way galaxy, because for some of these things, the outbursts probably happen every century or every 1,000 years or so. These variations help us in another way, because as I mentioned before, to use this ellipsoidal modulation to measure the inclination angle, you want as little optical emission from the accretion disk as possible. So what you want to do is you find out that you have a source when it goes into outburst, and then you wait until it turns off, and then you do all the follow-up measurements. So that's how we go about proving that we have black holes. We have a couple of other indirect techniques that people have suggested. And these are both related to the idea that neutron stars have a surface and black holes don't. So it turns out when they're bright, neutron stars have somewhat different X-ray spectra than black holes do. And probably this is because for a neutron star, if you remember, I said half of the energy that gets released gravitationally goes into making the disk rotate faster. Well, eventually you reach the surface of the neutron star, and then all of that energy has to be dissipated all of a sudden, because the disk is rotating a lot faster than any neutron star will rotate. And so when you do that, there's a boundary layer region, and that gives you an extra source of energy that you input, and it affects the shape of the spectrum of the accretion flow. The other thing that you could do is you can wait until the systems turn off. And so these are the lowest X-ray luminosity ever measured for particular systems, and it's done as a function of the orbital period. And if you want to know more about why it's done that way, ask me in the questions. So a lot of these black holes are not even detected when the outburst has ended, even with deep observations with the Chandra X-ray Observatory, which is the most sensitive X-ray telescope we have. And the neutron stars are all reasonably bright even when they've gotten to their faintest level. And this is, again, because the neutron star has a solid surface that can radiate power, whereas the black hole itself won't be emitting anything. And so if the accretion disk turns off, then there's just nothing to radiate there. Okay, and one other kind of indirect approach that we can use is we can use the radio emission from the jets from these systems. So these systems eject jets of material, and the further up the jet that you go, the lower the frequency of the radiation. So the furthest up part of the jet emits the radio emission. And it turns out that the black holes are the symbols that are plotted here, and the neutron stars tend to fall along this track or this track. So when the typical radioluminosity for an accreting black hole is higher than the typical radioluminosity for an accreting neutron star. And this isn't necessarily a rock solid case, especially up in this part of the diagram, but it seems to work pretty well. Okay, so I'm going to skip that slide. So the next thing that we can do is we can also start to look for these systems in other nearby galaxies. And this is an image from a paper I wrote quite a while ago now. This is an X-ray image of the galaxy NGC 4472. This is a galaxy that's about 16 megaparsecs away, or about 50 million light years away. It's the most luminous galaxy in the Virgo cluster of galaxies. And this is an optical image of the same galaxy here. And we have about 150 X-ray sources in this one image taken with the Chandra Observatory. And this was an image that was taken over the course of about half a day. And that's about the same number of X-ray binaries with low donor star masses, low mass donor stars, as we have discovered in the whole history of X-ray astronomy in the Milky Way galaxy. And so when you go to the other galaxies, you can detect a lot more sources. Now, most of these sources only have 10 or 15 X-ray photons detected, so you can't learn nearly as much about the sources, but they're all so far away that we can't do the mass estimates. But if you just want to find large numbers of objects, you could do them in the nearby galaxies. All right, and one of the other things that's interesting here is that if you look in the halo of this galaxy, you could see some bright point sources, and a lot of those are actually globular clusters that are in this galaxy. All right, so one of the things that going to the nearby galaxies opened up is the discovery of globular clusters with black holes in them. All right, and this is an image from the XMM Newton Observatory, and this is an observatory that has more collecting area than the Chandra X-ray Observatory. So if you detect a source, you get better data, but it has lower image quality, and that makes it have a higher background. And so it's not quite as sensitive as Chandra, but when you do get a detection, you can get a better detection. And it also has a bigger field of view for the imager, which was important for this project. So there's an X-ray source right here that in an optical image is right here. All right, and this optical object is a globular cluster, and the X-ray source was extremely luminous. All right, so we went and we looked at this object, and what we found was that this X-ray source also varied in brightness by a factor of about 7 over the course of a few hours. And this was important because, and the luminosity of this system is about 5 times 10 to the 39 ergs per second. So that's 5 times 10 to the 32 watts. And that's well above what we call the Eddington luminosity for a single neutron star. People had seen this in extragalactic globular clusters before, but what they hadn't seen before was the strong variability. And since a globular cluster has about 1 million stars in it, globular cluster could have had multiple X-ray binaries in it that had neutron stars in them, but the variability proves that at least most of the emission is coming from a single bright source. The other thing that was interesting about this object when we looked at it in detail was that we saw this very strong, very broad oxygen emission line. Okay, and we didn't see any emission lines from hydrogen. Because hydrogen is so abundant in the universe, and some of the hydrogen lines respond very well to anything that would make ionized gas, seeing this huge ratio of oxygen emission to hydrogen emission really tells us that there's little or no hydrogen in whatever is doing this. That the fact that this was happening in the same cluster as this black hole tells us it must be related to the black hole. Now, if you look at the velocities of these lines, right, so by looking at the width of the lines, you could take a delta lambda over lambda, and that gives you a fraction of the speed of light. And so in this case, delta lambda over lambda is about 1% of the speed of light, so about 3,000 kilometers per second. And that's an enormous speed for some kind of nebular gas. And we know this is nebular gas because this is a forbidden emission line. And so what we think is going on here is that we have a black hole that's trying to accrete gas at higher than the Eddington luminosity. And the Eddington luminosity is where radiation pressure and gravity balance one another. And so if you try to throw too much mass onto the black hole and it puts out too much power, that puts enough radiation pressure on some of the gas that you blow a wind out. And so that's what we think is going on here. And then the fact that we only have oxygen and not hydrogen is telling us that the donor star in this binary must be a star that doesn't have hydrogen in it. And in an old stellar population like globular clusters are, really the only possibility for that is that it's a white dwarf. So what we think we have here is a white dwarf black hole binary at a very short orbital period, so that its gravitational radiation is driving them together very quickly and causing a very high mass transfer rate that makes this system. All right, so now let me explain some of the excitement behind the idea of seeing black holes in globular clusters. So before our discovery of this system in 2007, there was a theoretical claim that globular clusters shouldn't have black holes in them. The idea behind that is that in a globular cluster, the stars try to approach something like a thermodynamic equilibrium. And so the heaviest stars will end up with the smallest velocities, so that all the stars have about the same energy, or at least they have a Maxwellian distribution of energies. So when you do that, the heaviest things end up in the center of the cluster, and those are the black holes. And if they're a lot heavier than everything else, then essentially you make a little black hole subcluster, and that little black hole subcluster won't have enough mass from anything else in the cluster coming into it to matter. So that subcluster will evolve on its own. And very small star clusters end up dissolving themselves over time. So this had been a theoretical idea. It was proposed that the black hole subcluster would end up forming in the center and then evaporating itself over time, and you wouldn't have any black holes left. We went out and found this object, and that got a lot of theorists to start redoing their calculations. And what they realized is that this process doesn't go to completion. You'll eject some of the black holes, but you won't eject all of them. All right, and now in the last 5 years or so, we've gotten to the point where some of the theorists are now saying that not only are black holes common in globular clusters, but the LIGO events that are from black holes are all from globular clusters. So I think that's a controversial point, but the idea that globular clusters are a good place to make merging black holes is not controversial. And the masses of some of these black holes that are merging in the LIGO data are so high that they can't be made from normal stellar evolution. So a natural way to try to make them is repeated mergers in a star cluster. All right, so that got our group, so I was involved with this paper too. That got us interested in looking for black holes in the Milky Way globular clusters. So we took a survey using the Very Large Array for radio data of a large number of globular clusters in the Milky Way galaxy. And we had a bunch of things that we were trying to do with the survey. The main goal when we first started doing it was to try to find intermediate mass black holes in the centers of globular clusters, and we didn't find any of those. And I think the fact that we didn't find any gives us a reasonably good argument that they either aren't there, or at least they're not common. What we did find was some objects that had radio properties that really look a lot like stellar mass black holes, and had X-ray properties that also agree with stellar mass black holes as an explanation, but not with neutron star binaries. Right, and so we found 2 of them in this cluster, M22. And then moving on, we started looking at this cluster, 47 Tucanae. And this is a star cluster that if you get into the southern hemisphere, you can see it with the naked eye. It's very close to the Magellanic Clouds. I think you probably can't see it from Bangladesh. Maybe it'd be right on the horizon at just the right time of day and right time of year. But it's at about minus 70 degrees declination, so it certainly won't be high above the horizon. But if you go just a little bit further south, you should be able to see it with the naked eye. All right, so we looked at this cluster, and this is an extremely well-studied cluster, but what nobody had done was to do good radio observations in it before. And again, we found a bright radio source in it. And then we looked at the counterpart of this, and it turns out that this object had been known for quite some time. Excuse me. And it's this particular star, and it had been classified as a cataclysmic variable star. And that's one of these binary systems, but with a white dwarf at the center of the accretion disk. But people hadn't paid too much attention to what it really was. And it was actually known that it was very bright in the X-rays compared to most cataclysmic variable stars. And so we started paying a little more attention to what it was. And what we realized is it has this extremely broad emission line here. And this is of a carbon line. And then we looked a little bit more carefully. And this system, like the first globular cluster black hole I showed you, has no hydrogen lines. So what we think we have here is another white dwarf black hole binary. And for this one, we know what the orbital period is. It's about 28 minutes. We're continuing to try to understand the system, but this is a really exciting object because this is getting close to the point where you might be able to detect gravitational waves from it when the space-based gravitational wave detectors go online. All right, so now I'm going to try to close up, and I might be finishing a little bit earlier than the allotted time, but hopefully you'll have a few more questions, and I'm happy to take a little bit of extra question time. Let's talk about what's happening nowadays that we can use to try to find black holes and what's happening in the near future. So one of the most exciting things happening nowadays is a satellite mission called EROSITA. And EROSITA is making a map of the entire sky in the X-ray band. And this is one of their first images. And fairly soon, they'll release the catalogs of data from half of the sky. So this is a partnership between Germany and Russia. And Germany has agreed that their half of the data will get released publicly. Russia hasn't yet, although I think they probably will eventually. They may just want to take a little bit longer to look through it before they make it available to the rest of the world. So EROSITA is detecting millions of X-ray sources all over the sky, including in the plane of the Milky Way galaxy. And what we can do is we could go do follow-up work on those and figure out which ones of those are new X-ray binaries. And the golden opportunity here is that with EROSITA, we'll be able to find some of these X-ray binaries before they have these giant accretion disk outbursts. And that, it remains to be seen how many new quiescent X-ray binaries we'll find this way, but probably we'll find more new X-ray binaries from EROSITA than we found from the history of X-ray astronomy up until EROSITA. And so this is a big opportunity. Looking forward, one of the things I'm really interested in doing is getting better X-ray all-sky monitors also. And so this is an image of a satellite called Strobex, which is something I've spent a lot of time working on the science case for. And we hope to pitch this to NASA as a real mission proposal sometime in the near future. So this is a plot from a paper by former graduate student of mine, Kavita Arur, who's now a postdoc at Georgia Tech. And this is the observed period distribution for the orbital periods of black hole X-ray binaries. and you can see this is pretty flat. Now, what we've found is that if you think a little bit more carefully about what are we missing in the sky, and you make corrections for all the selection biases in the discovery process for stellar mass black holes, it turns out we're missing a lot of short period systems, so things with periods less than about 10 hours. Some of those we're missing because we can't follow them up, but some of them we're missing because their X-ray outbursts aren't bright enough. And so if we make a better all-sky monitor like this one that would be on Strobex, we'd be able to go out and discover more of these fainter X-ray binaries in outburst, as well as the ones that will be discovered in quiescence by things like EROSITA. All right, one of the next things that we might want to do is to do better searches in the radio band. So I mentioned our survey of deep observations of Milky Way globular clusters with the Very Large Array. It turns out that was still sensitivity limited. If we could have made observations 10 or 100 times more sensitive than the ones we used, we would have been able to do a lot more detections of black hole candidates. So there's kind of two big projects to improve radio telescope quality. This is an image of, or an artist's impression of what the square kilometer array will look like. This is a Southern Hemisphere project. And then there's a next generation very large array project that's gaining momentum that would put something in North America that would be much more powerful than the current very large array. Right, so one thing that we could do is we could do more sensitive observations, but another thing that we could do that's illustrated by this figure here is because if we just go out and find a bunch of faint radio sources all over the Milky Way galaxy, we won't really know what they are, and probably most of them will be background quasars. And so if we want to sort out the background quasars from the interesting things in our own Milky Way galaxy, one of the things we can do is we can see if they move across the sky. And this is taking simulated square kilometer array data and then taking the difference of two images as a source moves. And you can see source on and then a negative source here from the subtraction. And so this is kind of a way that you can quickly detect moving objects. And with things like the next generation very large array and the square kilometer array, we might even be able to find isolated black holes that are accreting just from the interstellar medium in the Milky Way galaxy. So we might be able to find things that aren't in binary systems. All right, and so then in the optical band, there's some things that we can do also. So this is a plot from a paper by Todd Thompson and collaborators that came out a couple years ago, and this is kind of the tip of the iceberg. So they found an object using the apogee data from the Sloan Digital Sky Survey to look for something that was varying in radial velocity with time. And they were able to detect this detached black hole binary. So it's a binary star system with a black hole, and in this case, it's a red giant companion. And they're able to see the red giant orbiting around something, and they're able to do enough follow-up measurements that they could show that whatever it was orbiting around wasn't emitting any light, but was heavier than 3 solar masses. And so this is an idea that Virginia Trimble and Kip Thorne had proposed in the 1960s and hadn't had any success in implementing. And finally, 50 years later, it was made to work. So that's one thing that we'll get more of as we get some of these massive time domain spectroscopic surveys. Another thing that we'll get as we go forward is astrometric binaries. In particular, there's a satellite called Gaia in the sky right now that is repeatedly measuring the positions of every star in the sky above a certain brightness level. So I think it's around 1 billion stars that it measures. So it's repeatedly measuring their positions to very high precision. And now you actually might be able to see the stars orbiting on the plane of the sky using Gaia. Now, for the most part, the things where Gaia will see the stars orbiting on the plane of the sky are detached binaries where there's no mass transfer. And so this is giving us a window into a different way of finding black holes. And if the binary evolution process changes the mass of the mass distribution of black holes that gets produced, then we'll be able to see it as these kinds of techniques go forward. All right, so To summarize, stellar mass black holes are hard to find, and getting and understanding them requires a broad range of techniques. So it's one of the things that's really important if you go on and become an astronomer, is to really think about developing a broad set of tools and figure out what's the right tool for the job that you're interested in, and whether there is a single right tool or whether you need to try a whole bunch of different approaches and patch a solution together. So if you go into, say, condensed matter physics or particle physics, a lot of times there is a right way of doing something and you just go and do it. But in astronomy, a lot of times, because we're working with indirect approaches to everything that we try to do, you have to find 4 or 5 different ways to try to do something and then patch together what's really happening out of that, because all of them will have different selection biases. Right? So nearly the whole electromagnetic spectrum is vital for the cause of finding and understanding black holes. And then related to that, modeling is still a major effort as well, because all of these techniques have incompletenesses due to different reasons. And if you want to really go back and understand what the properties of all the black holes are, you want to figure out how to understand what you're missing and how to correct for that. All right, so that's what I wanted to say, and I'd be happy to take questions from you all now.
Yeah, thank you, sir, for your wonderful presentation, sir. We have got few questions, so if you allow, we can start our discussion session.
Oh yeah, absolutely, yeah. Do you want me to take the slides down or leave them up in case somebody wants to refer to one of them?
Yeah, you can keep your slide so that if anybody asks a question.
Okay, I minimize it so that I can see you all while you're speaking. But
so the first question: does the black holes and galaxy form together?
Do the black holes and the galaxies form together is the question. Okay, so I've been talking about stellar mass black holes the whole way. There are also supermassive black holes that are at the centers of galaxies, and that would be an entirely different seminar that somebody else would probably be better suited to give. So the supermassive black holes kind of evolve with the host galaxies, although the details of that are complicated. The stellar mass black holes form gradually over the lifetime of the galaxy. So the stellar mass black holes form from massive stars, and in galaxies like the Milky Way, the rate of formation of stars is roughly constant over time. So we're constantly forming new black holes. So I hope that was the answer to the question the person meant to ask.
Thank you, sir. There is another question. So what is the accretion disk?
What is the accretion disk?
Yeah.
Okay, so let me... Okay, so if I go back to this image, so this is the accretion disk. And so what the accretion disk is you take the matter that is spilling off of this star, and then it spirals inwards gradually. So that's what the accretion disk is. It's basically the stuff that's coming from one star and falling into or onto the other star. And you can get accretion disks around black holes, neutron stars, white dwarfs, and normal stars.
Okay, thank you. There is a similar question. What is the accretion stream? As we
yes. Okay. So the accretion stream in this diagram. So okay. So there's an outer radius for the accretion disk, which is basically where the angular momentum for the gas that's falling in right. So there's a certain amount of angular momentum that comes from this star relative to the orbit around the center of mass, and then you have a different amount of angular momentum in the orbit around here, right? So where the angular momentum of the gas falling in is enough to make a circular orbit, we call that the circularization radius, and that's usually about what the outer radius of the accretion disk is. But since this gas comes in and it's not being lost right at the circularization radius, it kind of free falls until it hits the outer part of the disk, and then it goes into the disk. So that's what the accretion stream is there.
Sir, thank you. So there is another question. What is the mechanism of high-speed jet from spinning axis of black hole?
Okay, so the mechanism for those relativistic jets is, I'd say it's an area where there's still some active research on it, but the basic idea is that if you follow the magnetohydrodynamic calculations, they tell you that matter should get thrown up the jet. Now, It's not clear observationally how important the spin of the black hole is for powering the jet. There are some theoretical ideas that what you're doing is you're getting the magnetic fields from the accretion disk kind of latch on to the ergosphere around the black hole, which is this region where you have frame dragging from general relativity. And you can use that to extract spin power from the black hole and put it into the jet. So there's a nice theoretical story there. The problem is if we look observationally at the powers of jets in different systems, they don't show much evidence for the black hole spins being important. So that's something where I think we need continued observational and theoretical work to understand whether it's the spin of the black hole is being tapped or just the rotational energy of the accretion disk gets funneled by magnetic fields up into the jet.
Okay, thank you, sir. This will be the last question. So,
okay.
Can we know the age of a black hole?
Sorry, how do we know what? The age?
Can we know the age of a black hole?
That's directly no. In some cases, we can get an estimate of that from what the companion star is like. And maybe from the mass of the black hole itself. So you can know that the black hole is young if its companion star is a very high mass star, and we have a few cases like that. And you can know the black hole is old if it's, for example, in a globular cluster, because there's no star formation in globular clusters anymore. But in most cases, you can only get a very crude estimate of the age of the black hole. I guess the other case where you might is if you had an association of the black hole with the supernova which formed it. So then you'd know that then you can use the age of the supernova remnant to figure out what the age of the black hole is. But yeah, most of the time you can't get the age of the black hole.
Okay, sir. Thank you for your wonderful presentation and discussion session. As we don't have any more questions, so we should conclude our discussion session, sir.
Okay, so, thank you all very much. And if anybody was shy or comes up with some questions later after they think about it a little bit more, please feel free to pass my email address on to the students.
Yeah, as the video will stay remain in YouTube and Facebook, I think anybody can ask question. If we'll get question, I will send to you by mail. So thanks again, sir, for giving us this opportunity to arrange such an important and exciting webinar with you, sir. So bye for today, and hopefully in near future we will arrange another webinar. And after the COVID, I will definitely invite you to visit our beautiful country.
Okay. All right. Thank you very much. Bye.
Bye, sir.